Uh, his research covers mathematical general relativity, including the Newtonian limit, post-Newtonian expansions, gravitating perfect fluids and elastic bodies, and more recently, the application of Fuchsian methods to global existence and the future stability problems. And today he's going to be talking to us about stable Big Bang singularity formulation in general relativity. So take it away, Todd.
Okay, great. Well, first I'd like to thank, before I get started, thank the organizers for inviting me to speak at the symposium. And today, as my title states, I'll talk about Big Bang singularity formation. So I'm not going to assume everybody necessarily knows everything about this sort of subject. So I'll start off slow and first look at some exact solutions that will be important that have Big Bangs in them. And then I'll try to explain what I mean by stable Big Bang formation. And then give a little bit of history, sort of where the problem came from, a few key results that lead up to sort of very recent work. So there's been in the last, I don't know, maybe about 6 or 7 years, some very exciting progress in this field. And then if there's time, at the end, I will talk, maybe I will say a little bit about some recent work with my collaborator, Florian Bayer, that we have on the subject. Okay, so okay, that's not. Oh, there we go. Okay, so before I can talk about Big Bang, you first have to fix a model where the Big Bang is going to happen. So for this talk, I'm going to restrict my attention to the Einstein scalar field equations. Okay, so that's these equations. So here, just to set things up, we have the R bar. So that's going to be our physical Ricci curvature tensor of some physical space-time metric G bar. Okay, so and this is going to be defined on some manifold, which I will call M bar. And then the equations we're solving is, well, we have this first equation, which is Einstein's equation. And then we have the second equation, which involves the scalar field. So phi is the scalar field. And if you haven't thought about things like this, how you should view this field phi is you should view it as some sort of elementary field that is sort of important near in the early universe and maybe less so important now. Okay, so this phi satisfies a wave equation, right? So it's linear in phi. So as far as phi is concerned, it satisfies a linear wave equation. But of course, the full equation is nonlinear because this box here is this wave operator, right? So there, the metric G enters nonlinearly into that. So that equation is nonlinear in G because we have inside, inside especially that second one, when you apply it to a scalar, which phi, you then get Christoffel symbols, which are nonlinear in the metric. And this is a self-gravitating system. So this is a matter field, and you think of it as self-gravitating via the Einstein equations. And then, of course, the matter acts as a source for the Einstein equations. Okay, so this is the system that we're going to be interested in throughout this talk. So just some terminology, when you have, when I say a scalar field space-time, what I mean is a solution to these equations, right? So just to be precise, to be a solution, what I first need is a manifold where both of these fields are defined, and then on that manifold, they need to satisfy the Einstein scalar field equations. If that all happens, then we say we have a scalar field space-time, okay? And of course, then now there's a question of scalar field spacetimes, because you can start thinking about, well, if I just restrict to an open set of a solution that I already have, well, that would be a scalar field space-time, right? So it comes with the set which it's defined on. Now, one thing one could try and do when looking at these equations is you could think about how do I make them simpler? And you could set phi equal to 0, and then you would just have the vacuum Einstein equations. And if you solve them, you get a vacuum spacetime. Now, I won't do that because even though the equations get simpler, this situation is much harder to analyze. And in fact, outside of some special symmetry classes of equations with some special symmetries, yeah, there are no techniques that allow you to analyze what's happening near the Big Bang for these equations. Somehow the dynamics is too complicated. You get this so-called mixed master chaotic type behavior. That's what you expect in general near the Big Bang. So I won't talk about these because basically there are no rigorous results on this. But I will try and say a little bit more about that later. So we will stick to these equations, and I'll try to describe why these behave better than the vacuum equations. And it's also, I guess, from a physical point of view, these equations are better because it's expected that there is some matter, at least some fundamental fields in the early universe, so you don't expect to have strict vacuum there. So this is in some sense going some direction towards the physical case in any event. Okay, so the first sort of solution or how to get a feeling for the Big Bang is we look for the simplest solutions with the Big Bang, and this is the FLRW scalar field solutions. So these will be solutions to the Einstein scalar field equations, and they're a particularly simple form, and they're ones that are exact that we can study. So what we have here is we have our physical, we have our space-time, and what we think of it is, well, it's just an interval of time, so 0 to infinity. So you should think of that as a time interval across a spatial manifold, which for us will be an n-1 torus. Okay, so here n is the space-time dimension, n-1 would be the spatial dimension. You can be happy enough to stick n equal 4 because that's the physical one, but we won't have any restrictions on n. Well, we will have restrictions on n. We'll be allowed to have n bigger than or equal to 3. Okay, but n equal 4, of course, is the most important. Okay, we then have our physical space-time metric, and how that is constructed. Well, we get an exact formula, which is just going to be this time. This time t, which you think of as a scalar function that lives on the space-time, but it's really just a coordinate on the interval 0 to infinity. So that's just the sum power depending on the dimension times by this metric g tilde. Now this metric g tilde is just this one here, and that's going to be a flat metric on that space. Okay, so it's an unphysical metric, and it's flat. So you can really see that this is just saying that the physical space-time metric is conformal to the flat metric. Okay, we also have the scalar field, so they'll have some constant dependent on the space-time dimension, and then times by logarithm of p. Okay, so that's the solution. You can now go check that by calculating by direct substitution and verifying that this satisfies the Einstein scalar field equation. Now, what makes a solution interesting is that and it gives an explanation of why I only go from 0 to infinity, is that if you just look at these formulas here, if I set t equal to 0 here, the metric becomes 0, the space-time metric. Well, that can't happen because the space-time metric to be well-defined has to be non-degenerate. So setting t equal to 0 is a problem. T greater than 0 is okay, but t equals 0 is a problem. Gets even more acute, of course, in the scalar field equation is as t goes to 0, this thing's going to blow up to minus infinity. Okay, so this solution is not well defined at t equals 0. And so something interesting is happening at t equals 0. There's something in our equations. Now, I'm going to belabor this point for a little bit because it's the picture that I want, okay, and how you should think about things. So first, I'm not going to be interested in all of this manifold, okay? So t here, you can think of this time getting smaller to the past bigger is to the future. So t going towards infinity is the future. We're not going to be interested in that, okay? What we're going to be interested in is picking a particular time, t naught. You can think of that being 1, for example. And we're going to think about going towards the past or in the contracting direction. So we're going to have t going smaller than that. So in your mind, you should always think about sort of the space-times we're dealing with as some interval of t naught or 1 to 0 across a spatial manifold t sub n. And geometrically, how we think about this is we think about this being a function defined on space-time that is a time function. So what we can do is we can use it to slice space-time. So our starting manifold, where this is just saying the level set of t would be equal to t naught. So that would be that t equal t naught constant hypersurface. That's going to be our initial surface. So I will call that sigma throughout this talk. Then we can slice the space-time with decreasing t, and what we get is a sequence of slices up the space-time, where the important part of here is you'll notice that at different times that we slice the space-time, they're all diffeomorphic to each other and diffeomorphic to the initial starting hypersurface. Okay, so that's all we can do. We can slice things down going towards 0, but not including 0 because our solution doesn't exist there. But one thing that does exist there is this function t. If you think of this as just a coordinate, it clearly can be extended smoothly to t equals 0, right? So we have this manifold, which is which is this manifold that I'll be interested in. Okay, so this is a piece of the physical space-time. And what we can do is we can then attach t equals 0 to this. So this is outside of space-time, okay? But we can still attach it. And in some sense, what we like to interpret this as, well, a couple things. When we attach it, one thing you notice is that it has the same topology as all the previous slices, okay? So that's important. So it's not like there's a singularity happening in the solution, but it's not like it's changing topology or doing something crazy there. We're just getting a nice progression in terms of topology. And it's also space-like in a certain sense, right? So each one of these preceding hypersurfaces were all space-like. And so we can sort of, in some sense, and there's a way to describe this a little bit more rigorously, we can interpret that final slice as space-like, even though it doesn't even exist inside our manifold. And our original metric doesn't exist there, but we can still call it space-like. And now a key point is what you can do is you can now take a look at some curvature invariants. So for example, I might want to take that curvature invariant where I just contract a Ricci scalar with it, a Ricci tensor with itself. And you can look at that, and that blows up as you approach, as t goes to 0. So as you approach that final slice, on that final slice, this curvature invariant blows up, okay? And so that's a picture you should have in your mind for what is a Big Bang. That picture, if it survives, okay? So this is this picture in this exact symmetry, but the question is, how can we sort of understand that this survives in a general setting? Okay, so just a little bit of history. So the FLRW spacetimes were discovered, I guess, in the 20s by, I guess, F and L of this, Friedman and Lemaitre. And then later, Robinson and Walker did some analysis of this. So already in the 20s, they discovered these solutions and noticed that they had this singularity in them. And it was, in the beginning, very, very problematic how to interpret this singularity. Is it real? Is it something we should take seriously? Does it have any physical meaning? And so there were discussions about this right after it. Okay, it became clear after a while that these were important solutions. Now they're very special solutions, and they're exactly solvable. In particular, as Elliot said in his talk earlier, these FLRW solutions are spatially homogeneous and isotropic. Okay, so this makes them very special. Now the universe isn't spatially homogeneous and isotropic, so these can't describe the exact universe, but what you can do with them is one thing you might want to do is treat them as some solution to which you do linear perturbation theory around to try and sort of characterize solutions that are almost spatially homogeneous and isotropic, but not quite. And then you assume that the deviations are small. And if that's the case, then hopefully you can use linear perturbation theory then to discuss spacetimes that deviate from this spatial homogeneity and isotropy by a small amount, which maybe will describe our universe, okay? And so this actually forms some of the foundations of modern cosmologies. Certainly this is linear perturbation plus FLRW is extremely important. Now, there's a question though, that was already sort of discussed in the 20s, and for a long time, the question came down to you might be able to have these solutions, but are they physically relevant? Okay, so physically relevant here means when they first encountered these, there were some arguments, fairly convincing ones too, heuristic arguments that would say that these solutions, the Big Bang or the singularity in them was due to the assumption of exact homogeneity. Okay, and so there were some arguments that if you just took some solution that was slightly inhomogeneous, that would all disappear, okay, and everything would be fine. So if that was the case, then you would never, in principle, ever see these in a physical system, these singularities. So the question, to what extent are these solutions, can you see them if you look at nearby solutions which are inhomogeneous? Do they survive? Okay, now this is something that can't be answered by linear perturbation theory. This is a nonlinear effect, so you really have to analyze the full nonlinear equations to try and figure out what's going on. Okay, so this leads to sort of the main sort of question of my talk is that are FLRW spacetimes and their Big Bang singularities stable under perturbation, nonlinear perturbation? So that's the key. So I want to discuss this, but before I can really discuss this, I have to do a little bit of background, because the word stable here, what do I mean by that? Okay, so to do this, we need to discuss the initial value problem for the Einstein equations to get an idea of what do I mean by stable under nonlinear perturbations. Okay, so the initial value problem. So for people who don't think in the initial value problem world, this is an introduction. And if you do, well, then that's okay. You will understand what I'm talking about. But this is sort of the way that I think about the Einstein equations, is almost exclusively as an initial value problem. Okay. So before I talk about the initial value problem, though, first what I want to do is just slightly reformulate the equations that I'm solving, and this will just be mostly cosmetic, okay? So what I'm going to do is, instead of considering the Einstein scalar field equations, I'm going to consider these equations, which I'll call the conformal Einstein scalar field equations. Now, how they are, they're completely equivalent to the Einstein scalar field equations, except I parameterize, rather than using the physical metric, I'm going to use a conformal metric, G, which is related by that formula. And rather than using this scalar field, I'm going to use this scalar field, okay? Now, this turns out to be helpful from the point of view of analysis. It also, you can see, easily locates the FLRW solution, because if this metric was flat and this was a time coordinate, then we would have the FLRW solution. It turns out this parameterization also becomes useful for analyzing perturbations of the FLRW solution, nonlinear perturbations. Okay, so what I'm interested in is finding solutions to this system of equations, okay? And then we want to analyze, try and find, are there Big Bangs in solutions to this that are near, sort of starting near, in some sense, FLRW solution. Okay, so we want to find solutions to this. So from the initial value point of view, the first thing we have to do is specify initial data. So how we do this is we pick an initial hypersurface. So this is just some space-like hypersurface inside your space-time. Of course, you don't even have a space-time yet, so you have to sort of decide on what you mean by this, but there's a way you can sort of describe this without necessarily needing an ambient space-time. Okay, and then what we have is, well, we need some sort of notion of normal, so time going in the direction of time, and I'm going to specify that by some vector field n. So this will be my time like normal to the thing. Then what we need to do is, well, to get the evolution problem started, we need to specify the space-time metric. So I'll just think of this naively as a bunch of functions. So we could think of this as a matrix of functions. So I specify some given set of matrix functions on here. Okay. And then what I need is also essentially the time derivative. So this would be the Lie derivative in the normal direction of the space-time metric, or of the conformal metric. And then I can also just prescribe whatever I want for that on the initial hypersurface. I have this scalar field, which is which I also have to give data for. So I give it some initial data by picking some function on here. And then again, for the time derivative, I pick some function on there. Okay, so I get all of that initial data, and that's what I need to start running to figure out what to basically evolve this, use the Einstein equations to evolve this initial data off this hypersurface to get a solution of the conformal Einstein scalar field equation. Okay. Now there's one complication, is that this initial data, so that's the stuff I get to choose. There are some conditions there, but I won't really worry about it. But the most important condition is that you can't pick those freely. You have to satisfy an initial, you have to satisfy a so-called constraint equation. So I'll call that the gravitational constraint equation. Okay, so this is the set of equations that your initial data needs to satisfy. And I won't talk about really about how one goes about solving this or analyzing this problem. It has a whole life of its own. It's a huge area in its own right. What I will just do is that I will assume that we have initial data that satisfies this equation. Now, at least near the FLRW solution, by near FLRW initial data, so you could think about taking your FLRW solution, restricting it to a hypersurface, say a t equal constant, that creates initial data. Now, in the neighborhood of that initial data, you can solve this problem. Okay, so we're not talking about the empty set, which is good. All right, so once we've specified our initial data, then, well, what we do is not all that initial data is of interest, because only the stuff that satisfies the gravitational constraints turns out to be important. Okay, and I will give that stuff a name, and that's called the geometric initial data. So out of all of the initial data, I can locate some subset of the data. Okay, so I have the scalar field on the initial hypersurface, its time derivative on the initial hypersurface, and then what else is important turns out to be this 3 metric. So this H is a 3 metric on the initial hypersurface that you obtain by just restricting the conformal metric to the hypersurface by pulling it back or just taking the spatial components. And then you have this other thing called the second fundamental form, which is derived from this formula here, and you can construct all these fields out of the space-time metric. But the important part to take away is K is really just like the time derivative of the spatial component of the conformal metric. Okay, so the key point about that is that this initial data is the physical initial data. All the rest of the initial data is gauge, and it doesn't matter how you choose it. Okay, if I choose it one way, you choose it another way, as long as our geometric initial data is the same, we have the same physical solution. They will only differ by a diffeomorphism, which we can't tell. There's no experiment that will tell that these are two different solutions. Okay, so geometric initial data is the only thing we care about. The rest of it, we can pick how we like. Now, important thing is to sort of stress this is that the gravitational constraint equations, which constrain the physical initial data, can be written totally in terms of this geometric initial data. Okay, so now that we have our initial data fixed, the next time we need to do is we need to construct some space-time so that when we restrict it to the initial hypersurface, it agrees with that initial data. So this is a local in time existence theorem for this initial data. So the first sort of local in time existence theory, was first discovered by Choquet-Bruhat in 1952, and she did it for vacuum. Since then, people have figured out how to do this for the Einstein equations plus various matter sources, including these conformal, including the Einstein scalar field equation. Okay, and so what this local in time existence result gives you is two things. One is it gives you space-time. So it will say that there is some region of space-time. And what you should think about this is essentially a time interval T0 to T1 cross a space manifold, okay? But geometrically, how we think about it is we get a time function. So we get a time function, we get this manifold. This time function can be used to slice the manifold up into a bunch of leaves. The first leaf, which is where we set our time function equal to T0, which we can think of as our starting time, that will be our initial hypersurface where we stick the initial data. And then we will think about our time getting smaller and we slice the space-time and it will be diffeomorphic. So our first time slice will just be our initial hypersurface, and our other time slices that go between these two range of times will be diffeomorphic to our initial starting hypersurface. Okay, so we get this. That's part one of this local in time existence theory. And why it's called local in time is you somehow think about this as somehow small. It's close to T0. So you might get somewhere, but maybe not that far. Okay, and then the second part of the theorem is then you get the existence of a conformal metric and a scalar field, because I'm interested in solving the conformal scalar Einstein scalar field equation. So the right existence theory gets the existence of these fields that live on this space-time, right? And they do a couple things. So one, the triple is a conformal scalar field spacetime. So it is a solution on that manifold. And two, if you restrict that solution back to the initial hypersurface, it will induce initial data that agrees with the starting geometric initial data. Okay. Now, one interesting thing about this problem is that you might have started with whatever non sort of geometric initial data, the rest of it. When you construct the solution this way and you restrict back, there's no guarantee you get back all the same initial data. That's not guaranteed. Okay, but it's guaranteed to give you back the same geometric initial data. Okay, so that's our local existence theory. But now what we want to know is that the biggest that we can have? Okay, so for this, we need the notion of a maximal development. So what that is you can think about, I have some initial hypersurface. I sort of use this local existence to get a small bit of space-time that sort of, you might say, okay, so whoops, here is my, maybe my initial hypersurface, and then I might get a small piece of space-time, you know, something like that, where the solution exists. Okay, so that's the one thing, but then maybe I can take, you know, a piece here, because you can do this in a local way, and maybe I can extend this piece here to get some more, and, you know, I can extend that piece some more, and then you can try and extend using this local existence theory again and again and again. Okay, so there is a notion in which you can do this until you can't anymore, because something goes wrong. And that biggest one you can do this is called the maximal development. Okay, so there's a notion which you use this local existence theory to build up this maximal solution that can possibly exist given your initial data. I won't talk about it because there is some technicalities to it, but you just think about it's the biggest space-time that can be generated in a reasonable sense from your initial data, okay? And so given some initial data, you will think that it generates some maximal space-time, and that's the thing we're going to be interested in. What is the maximal space-time that's generated from our given geometric initial data? So in general, trying to answer this problem is impossible, okay? So it's hopeless to do this. Where it isn't hopeless is if you maybe know something about one particular solution, you know its behavior, and maybe you understand the maximal development of a particular solution, then you might be able to look at nearby initial data and also hope to understand its maximal development. And so that's one of the big sort of thrusts of modern mathematical relativity, is to try and understand where you can the maximal development of spacetimes for given initial data sets under certain restrictions. Okay. So that's what we're going to need to do to understand this black hole problem, because what we're going to do is we're going to take our FLRW solution, we're going to restrict it to a hypersurface that induces initial data there. We're then going to look for initial data in a neighborhood of that hypersurface, and we're going to look at the maximal development of that initial data to the past. And we're going to go, well, what happens? Okay, so this is going to be FLRW Big Bang stability, right? So we're back to the question now, are FLRW spacetimes and their Big Bang singularity stable under nonlinear perturbations? Okay, so let's go through a bit of the history of this, just a few key results. So they were discovered in the 1920s, and some answers between, for a while, people could make some rigorous results, but they always relied on some symmetry assumptions or some other very restrictive assumptions. And the first answer to this question, are FLRW spacetimes and their Big Bangs stable, comes from the Hawking's 1967 singularity theorem, which should really be called not a singularity theorem, but an incompleteness theorem, okay? So what this theorem says is it guarantees that if you have a cosmological spacetime, then if you look in the contracting direction, which you could think to the past, it must be geodesically incomplete if the initial data satisfies certain conditions, which allow for extremely large classes of initial data. And also if you have matter fields or vacuum, there's a large class of these to which this theorem also applies. And what it says is that your space-time must be geodesically incomplete. So how you should think about this is I have, say, a hypersurface. I can put some initial data on it, and then I can construct to the past the maximal development. And then what Hawking's theorem says is that for large classes of initial data, the maximal development inside it, there will exist one curve, one time-like curve going towards the past that will run off the manifold or end somehow in finite time. And so this is Hawking's singularity theorem, so it should really be called an incompleteness theorem because we have no idea if there's a singularity there or not. It just says it ends. It says nothing more than that. So people widely anticipate that this is going to be due to a curvature singularity, right? So we want an answer why something should stop it. Now, what's stopping it? The FLRW solution, well, we have some nice singularities there, so maybe they're the same type when you look at other data, and what's causing this is a curvature singularity, okay? So until very recently, there was no answer for this question at all. So nobody had any rigorous result that could state definitively that this is what's happening that applied to non sort of generic initial data, say any data in a neighborhood of the FLRW solution. Okay, now the next piece of work, which was very influential, is the so-called BKL conjecture from the 1970s. So it is a general statement about singularities in the Einstein equations. So the general postulate is that generically, and that singularities should be space-like and oscillatory. Okay, so here space-like and oscillatory, and I left out the word generic, but none of them are really defined rigorously, right? So this is a physics conjecture. But nonetheless, it is very convincing how they, if you look at their arguments about why they say this, it is, you know, it's certainly reasonable to make this conjecture. Now, here oscillatory means on the approach to the singularity, the fields that you have will oscillate. Okay, and in fact, they're known to, one expects that they not only just oscillate in a regular manner, but things are chaotic. Okay, so space-time can be quite complicated near singularities. Now, one thing is, and in particular near Big Bang singularities. Now, one thing is for sure is this is known not to be true. So this conjecture can't hold in as wide of generality as they say. And this is due to De Fermos and Luke, who showed that there exists sort of non-space-like singularities and open sets of initial data that lead to these. Okay, so this is not a true, this can't be completely true. There's very little rigorous results supporting it. There's only homogeneous work in the homogeneous setting where the Einstein equations reduce to ODEs. And there you have ODE theory, which is much more powerful than PDE theory, okay? And there it's been shown that this conjecture is true under certain assumptions, or certain conditions, but the important part is you can analyze the oscillatory behavior near singularities using ODE techniques. But already this is at the edge of what people can do with ODEs. So when you transition to non-homogeneous spacetimes and then you have to deal with the PDEs, it's somehow beyond our abilities right now to analyze what's happening near these big bangs. Okay, so there's also some but limited numerical simulations that support this conjecture. Okay. Even though there's not much supporting it, and it's also known not strictly to be true, people still expect this to be true for maybe under certain extra conditions, but for extremely wide class of spacetimes, this should be true. So it's still a guiding sort of idea in the field. Okay, so now what's going to help us out, because we cannot analyze oscillatory behavior around a singularity, we're going to look for, there happens to be situations, so certain classes of initial data and certain matter fields that lead to this oscillatory becomes monotonic, okay? So it's no longer oscillatory, but it's actually just monotonic. And this, when this happens, this behavior is called asymptotically velocity term dominated, or AVTD singularity. So on approach to the singularities, the fields, they might blow up, but they're going to do it monotonically. Like you should think of some power of t, sort of a power law blow up, or a power law going to zero, something going degenerate, something like that. So it's really the fact that this is where in the non-homogeneous setting right now, we have a chance to sort of understand what's going on near singularities. Okay, so now what I want to do is now talk about the first sort of rigorous result that since the 20s and Hawking singularity theorem in the 60s, where people were able to answer, do there exist sort of with no symmetry assumptions, other spacetimes with big bangs, okay, that look where you, well, that basically have the same features as the FLRW one, okay? And so first I'll say sort of in words what the stability means. So just to recap, what we have is we think about, we have an initial hypersurface, and for the theorem that I'm going to state, it needs to be diffeomorphic to the n-1 torus, okay? Now, if you have an initial hypersurface that, then you take the FLRW solution, you get geometric initial data there. Now what you do is you look for initial data, which is geometric initial data close to the FLRW. So not exactly FLRW, but close. So this would be initial data for an inhomogeneous spacetime in general. And then you will say that this thing is going to be stable if the same picture holds. So what you should be able to do is show that there exists a maximal development to the past, and you should be able to show the existence of a time function that slices the space-time into decreasing time. So we artificially call T naught the first hypersurface, and we'll assume our time function is defined from T naught all the way to 0, but not including 0. And you should be able to slice this. Each one of the slices should be space-like, and they should be also diffeomorphic to the starting one. Okay. Now, then what you should be able to do is show that this time function is regular enough that it extends to t equals 0. Now, all of this is actually hard to do for reasons that we could talk about, but you can think about it right now. If I give you a random time function that you're going to use to describe space, how do you know that it's going to hit that it's going to be t equals 0 on if you had a singularity? You don't know a priori when you're starting right now, when you're just trying to figure out how am I going to slice the space, is that if your singularity is going to appear as a constant time hypersurface. In general, you expect this not to happen. Okay, so finding a time function that does this is one big part of the problem. And then having the singularity happen all at t equals 0 is another really challenging issue. Okay, and then the last thing you need is you need one of the curvature invariants of the physical space-time needs to be blowing up as you approach that final hypersurface. So if that picture happens for a full set of initial data in some neighborhood, it may be really close, then you say that the Big Bang, then you would say that the FLRW Big Bang is stable, right? Because that would exhibit open set of initial data around the FLRW solution where the picture survives. So this looks like an FLRW Big Bang. So the first people to prove this was Rodniansky and Speck. So this is in 2018, and they assumed if the dimension, space-time dimension was greater than 4, then the FLRW scalar field Big Bang is stable. So this is non-linearly stable. And they also showed that the singularity is AVT. Has this AVTD behavior. And in fact, that's the only reason why you can prove this theorem is because it does have this. And there you need the scalar field to be non-trivial. This cannot be vacuum. Now, one thing interesting about their proof is that they introduced this time function T. It's a geometric one. And what it does is K would be the mean curvature, the trace of K would be the mean curvature of each of the slices. So they're using the sort of geometry of the slice to introduce a time. Okay, so this has very nice properties, but one of the problems is that this relies, it introduces a non-local element into the theorem. So it means that if they change their initial data, say a little bit here, they don't know that it doesn't affect the whole singularity. So there's a question is, if I localize changes on the initial hypersurface, how much does this really have to affect what happens on the singular surface? Okay. So this is not localizable, and that's due to this choice of essentially time coordinate that they're using. All right, so maybe I'll just say in the last 5 minutes a quick word. So this is where my collaborator Florian Bayer, we went back and revisited this problem, and we wanted to see if it's possible to look at a localized version. Okay, so what does a localized FLRW Big Bang stability looks like? Well, it looks basically the same thing. We want the same thing is we have the starting hypersurface sigma, but what we do is we don't look at the whole hypersurface. We only look at a subset. And we just want on that subset, the initial data to be close to FLRW. So outside of the subset, it could be absolutely huge. They're extremely far away from FLRW. We don't really care. But what picture we want to survive is the following. If we look at the maximal development of this initial data, which we have no chance to understand, because out here, you know, if we take extremely large initial data, we won't be able to understand that. But the point is, if you can localize, then it means that you don't have to understand everything that's happening everywhere. What you do is you get sort of like a cone going towards back. And this is, we're exploiting the finite propagation speed of the Einstein equations, which exists in there. But you have to use the right way of gauge reducing the equations in order to exploit this finite propagation speed. So we found a proof that does this. And basically it says that we get this localized region where we can get a big bang happening, at least on a portion of the maximal development, right? So whatever this maximal development looked like, we have no idea what it looks like out here, but at least here we know a portion of the boundary of the space-time is going to look like an FLRW Big Bang. Okay, so if you can do that, then you would say that your FLRW Big Bang is locally stable. And so that's what we were able to prove. And for some reason, we were able to do it for dimensions 3 greater, whereas Rodnyansky and Speck had 4 greater. And I'm not sure if that was just because they just didn't check their proof carefully enough, or if there's really a problem there. So one thing I will leave is why can we do this? And it's because we use a different time function, number one. So that's one of the key things, is we use the scalar field as its own time. So the value of the scalar field, this tau, it becomes the time that we use to slice the spacetime. And this makes sense from the FLRW point of view, because in the FLRW exact solution, this tau is exactly t, right? So it's using that. And then we also use a wave gauge. For people who know about these things, this is a way to make the Einstein equations gauge reduce them so that it's explicitly has finite propagations. Okay, so I think that's enough for me, and I will stop there.
Okay, thank you, Todd. So I guess I'll ask if there are any questions for Todd.
This is quite a bit earlier in your talk, but you were saying that the Hawking, the result by Hawking, the incompleteness theorem, has at least one geodesically incomplete, is it time-like ray that goes backwards. Is there any other known reason why that would be geodesically incomplete, other than there being a singularity there?
Well, I don't know. You could have something like a Cauchy high horizon form, right? Where so yes, there are other reasons why this could happen.
Why are they not? Why is that not seen as much, or as clear of a possibility as singularity information? Well,
I guess, like, say, if you're in the neighborhood of FLRW, you'd like to believe, like, if you believe in this, the first guess is that picture is going to survive somehow perturbation, right? Like that might be the initial guess, is that it does survive. And so I guess that's why people initially have that feeling, right? Yeah. But if you go very far from it, I guess, who can say what's going to happen?
I have a question. So you were talking about the whole BKL conjecture and how you expect chaotic behavior and all this stuff. But in both of these proofs by Speck and Rodnyansky and yourself, you have the AV-TD behavior, so they're not part of the BKL.
Well, no, they are, because they are examples of trivial oscillatory
right?
solutions,
Okay.
Right. So no.
So it's the most simple case.
Yeah, they're the simplest case possible,
right,
of the BKL conjecture.
Yeah.
But you don't expect those to hold. If you want to analyze all types of matter sources and all types of, in particular vacuum, say, then like in vacuum, if you have Gaudy symmetry or polarized Gaudy, then then you do get this ABTD behavior as you go towards the singularity. But if you get rid of it, it's expected that you will have this mixed master chaotic behavior, oscillatory behavior as you go backwards towards the singularity. So they'll be very complicated.
So is this ABT behavior just because you happen to be choosing what the FLRW starting?
Yeah, well, it's two things. It's one that we have this scalar field and we pick particular initial data that it's not trivial.
Yeah.
And also that we're not too far from the FLRW. Yeah. So even if you had this scalar field and you go very far from it, I guess you would then expect to again be in this sort of mixed master regime. Oscillatory.
I think there's also a question in the chat.
I don't know. Okay, I'm trying to read this question about by Colin. I'm not really sure. For me, how I interpret it is I just interpret it as a matter, and then of course once it is a matter source, then it enters the Einstein equations in the usual way via the stress energy tensor. In the proof, I've just mixed them up because I've artificially introduced this conformal metric. But that's the only important thing is not the conformal metric, it's the physical metric. But for the analysis, the conformal metric, for us at least, turned out to be much more convenient. And also using this tau scalar field rather than the original sort of more usual phi scalar field was also useful for us. I hope that answers your question.
Was there another question? Oh.
Sure.
Maybe you should read out the question.
Okay, so this is by Ming Chen. So Ming wants me to talk a little bit more about the conformal scale field equations. What is the conformal factor of the metric? What is its form in the line element in the and consider the massive scalar field. How will the mass affect the conformal transformations? Thank you very much. Okay, so one thing is that you should think about here is the conformal scale field doesn't have any really physical any physical meaning. It is merely an analytic tool to understand the physical Einstein equations. So here, the important part is that what we have is the physical variables are those. So the physical metric and, well, okay, this one doesn't matter because it doesn't matter how but that's sort of the usual parameterization of the scalar field. Those satisfy the regular Einstein scalar field equations. Now, I'm free to parameterize the metric how I want, and I just choose to parameterize it this way because it's guided by the FLRW exact solution, how it's represented, and it turns out to make the analysis quite nice. But there's nothing special about this. One doesn't need to do this. It just turns out to be useful. So I don't think there's any special meaning for that side. The only meaning for this system is these equations, right? These are the only equations that have the physical meaning there, and the G bar is what we use to measure proper lengths and proper distances. So that's I guess, how you should really interpret these solutions.
Cool. Are there any more questions for Todd? So.
I don't think so.
If not, thank you once again, Todd. And we will be reconvening at 7 p.m. for Chris Stevens' talk online. Oh, sorry. Yes, there's a there's a collaboration session now, but yeah. So I'll let Louis organize that. So. Do you want to hook up?